Well, hello and welcome everyone. This is Mr. Robinson and this is your Algebra 1 Spring Final Exam video review. Before I get into anything, let me just talk a little bit about how this is going to work. It is nearly midnight right now. This is the time that I need to get this recorded so I can get it up for you guys. And my godparents are in town and they're asleep. Combined with me and my throat issues, as you know, I've had it for over 3 weeks now. I'm gonna have to talk pretty low. Okay, it's almost like, I know you guys know those AMSR things, or I forget what it's called, ASMR. It's gonna kind of be like that, only I don't have a really nice soothing voice for it. But that's okay, as long as you can hear me and as long as it makes sense. I will apologize if I cough a lot of times during this video. I'm gonna have to turn away from the mic to do that. Okay, now because it is almost midnight, I do want to make this as short as possible, but you know, there are no guarantees with this kind of thing. Here are the general topics covered. Exponential functions, that was Chapter 6. Polynomials was Chapter 7. Quadratic equations, Chapter 9. Statistics, Chapter 11. We also covered Chapter 8, and here you're going to see a breakdown of what units were there when we did graphing, though I'm not going to do much graphing with quadratics here. And you're going to see 5 example problems per section here, per chapter. Okay? All right, let's see. Okay, here's the breakdown of your exam here. There are 51 multiple choice questions and 5 free response. None are necessarily related to each other at all. The free response questions, you're going to get a Chapter 6 free response question, Chapter 8, which means graphing, Chapter 9, solving for x in a quadratic, and 2 different Chapter 11 questions. So 2 free response questions involving stat things. Expect to be able to have to calculate some sort of like mean, median, mode kind of thing, or to draw a box and whisker plot or a histogram, you know, something of that nature. Expect something along those lines. Now it's an hour, 50-minute final. It's 110 minutes. You have 56 problems, 51 multiple choice, 5 free response. If you double 56, you get 112. That is more than 110. That means you have less than 2 minutes per problem. Now, that doesn't mean that, you know, you can't spend 3 minutes on a problem. It just means that make sure that you are efficient enough to do some of the problems in pretty good time so that you have time for those other ones. Pace yourselves accordingly. You're going to be given the multiple choice and the free response questions at the same time. Okay, so what I would do is I would look at what the free response questions are to begin with. I'm not saying do them first. I'm saying note what kind of problems they are. That way, when you do multiple choice questions, which have answer, you know, the answers are there somewhere, you know what I mean? Like it's one of your options. You can then go to the free response one after that that might tie into it, right? Say there's a Chapter 8 one on graphing. And say there's a multiple choice question that says which of the following represents a graph that matches this equation. And you see 4 different graphs and you kind of determine your answer and you can kind of find out how that answer helps you on the free response and then maybe you can help give yourself a graph there. Stuff like that. That's kind of what I mean. They can help you. General multiple choice tips here only work until you know the answer. So remember, you have a time constraint here. Let's say you're trying to solve like a quadratic equation and you know that one of the answers has to be x equals 0, you know, because maybe it's a problem that looks like this. So zero product property says x equals 0. Now obviously it looks like the other answer is 5, but let's say in the multiple choice there's only one answer that has a selection of 0 for x in it. Well, you don't have to do anything else. Once you found this answer, you can kind of just move on from there, if that makes sense. However, be sure that your answer is also the correct one. So just because your answer appeared somewhere, you know, kind of after that, make sure that the other ones don't work as well, because there might be other x equals 0s, right? You might see x equals 0 on A, but D also has x equals 0 alongside another answer. So be very, very careful. Just make sure that yours is the correct one before moving on. Don't just look at A and say, oh yeah, you know, that sounds good. There's probably a better answer somewhere down the line that you just got to make sure of. So those are my tips for you. Okay, so you have this final outline for yourself here. What I have is this checklist thing. You see these ones that are marked in red, kind of a maroon here. These are the things that will be covered in this video. That means that these will not be covered in this video, at least not to the full extent of answering the questions that I'm doing. So take a look at these, and I'll show this at the very end before I close out again, so you can see them and say, okay, it makes a little bit of sense that those are actually jumping into here. And again, I'm only going over 20 questions, but my 20 questions, I will be doing enough that will be covering these things in some form. So just keep that in mind. I will be covering all of these 4 because these 5 questions were from your take-home quiz that had all of these different kinds of things. Okay, without further ado, I'm actually going to get started right now, right at midnight. Here we go. The first question I'm going to do is I'm going to evaluate this expression. And this is negative 32 to the 3/5 power. And that does mean in the parentheses here that the negative is a part of this. Well, the conversion that happens here is that the denominator of the exponent actually represents the root. It represents the root of this value here. So that 5 I'm going to put right here. This means the 5th root of. Negative 32 is actually what goes inside here, and I'm still going to wrap it in parentheses because I still have this 3 I want to take care of. And it looks like that. It says the 5th root of negative 32 quantity cubed. That means I can cube negative 32, and then I can take the 5th root of that number. Now, I want to let you know 2 things beforehand here. Number 1, I'm not going to end up doing it this way. I'm actually going to go and do the 5th root of negative 32 first, and then I'm going to cube it because cubing this number would make it extremely large, something that I don't want to have to take care of, and I wouldn't know what the 5th root of that is anyway. But if I take the 5th root first, then I get a smaller number, and I know what the 5th root of this number is, and then I can cube it. So that's number 1. Number 2, and I'm going to jump into this in just a moment with this problem as well, by changing a number, you're allowed to take the 5th root of a negative number. Okay, I can't take the square root of a negative number, but I could take the 5th root of a negative number. That is very possible. Because what does it mean when you take the 5th root of something? It asks what times what times what times what times what equals negative 32. And if you're multiplying 5 different things, an odd number, that means your answer can be odd, right? You can do a negative times a negative times a negative times a negative times a negative, and that does equal a negative. Now, what is that number? It happens to be 2, or negative 2 rather. Negative 2 times negative 2 is positive 4, times another negative 2 is negative 8, times another negative 2 is positive 16, times another negative 2 is negative 32. So if negative 2 to the 5th power is negative 32, then that must mean that the 5th root of negative 32 is negative 2. So there's the negative 2 inside here. Now I need to cube that value. And as we know, negative 2 cubed, these 3 things together right here that multiply, that becomes negative 8. And that is your answer. Now, a couple things with this. I did make mention in the very beginning that the 32 is negative. That is the thing that's being cubed. This is a different problem. Negative 32 to the 3/5 power like this is not the same thing as this here. Now, these both have the same answer because it just so happens that the result of these are both negative 8. However, even if you want to say that they're equal, here are 2 that are definitely not equal. What if I did negative 32 to the 3/2 power and negative 32 to the 3/2 power like this? These are definitely not equal. The main reason is this. If I convert this into a radical, then it will appear as the square root of negative 32 cubed. Now, whether I cube it or take the square root first isn't going to matter, because when I take the square root, eventually I'll be doing it of a negative number, and you can't do that. You cannot take the square root of a negative number, so this has no value. This has no value. I can do it in the calculator as well. This one, however, has a value. If you want to know what it is, it would be this. The negative is not being applied with the square root. This would be negative square root of 32 and then cubed, something like that. Okay. Now I'm not going to do the whole thing, but the square root of 32, that would be 4 root 2, I believe. So negative 4 root 2, you would cube that value, and then you'd get what you'd get. Oh, I can do this with you here. I think it would be negative 128 root 2. Notice the negative stayed on the outside the entire time. This has no value. This has this value right here. So whether it's in the parentheses or not is a crucial portion of this problem. This particular problem, it was not crucial because these actually are the same thing. But you don't want to treat them the same because you run into one like this where they're not the same. Got to be very careful there. Just like negative 4 squared is not equal to negative 4 quantity squared. This is negative 16. This is positive 16. Not the same. Keep that in mind. So if I'm to land on your answer again, what it actually is, this answer is negative 8. I know I jumped around, but of course the whole point is to teach everything around this type of problem and not just to tell you how to do this one problem. Okay, simplify the expression, write your answer using only positive exponents. So what we have here, and I'm going to rewrite this just a little bit. I'm going to get the 2 and the c to the 4th completely separated by a multiplication there. Make sure that those parentheses don't look so darn big. And that's what we're looking at. 2c to the 4th over 5, all raised to the negative 3rd power. Now, a couple properties can be used in play. And remember, these are the kinds of problems where there's more than one way to do it. So, let's see what we can do best. What I'm going to first start with is the property that says that this negative 3 can apply and result as an exponent to any portion of a product or a fraction here. Not distribute, unless I use air quotes, but what I can do is I can take the negative 3 and have 2 raised to that value. I can take the negative 3 and have c to the 4th raised to that value. And I can take the negative 3 and have the 5 raised to that value. And all of this is very proper. It is okay to do. It is very allowed. This is the mathematical necessity. Okay, negative exponents do not mean negative numbers. What they do mean, though, is that this is how many times these numbers divide. Divide and divide. Now, if you divide in a denominator, that means multiply in a numerator. So the 5 to the negative 3rd is actually going to be jumping up here. And what's going to happen there is you're going to get a 5 to the positive 3rd power written on the top. On the bottom, what happens is the 2 to the negative 3rd comes down to become 2 to the positive 3rd. Again, dividing by 2 3 times, is the same thing as multiplying by 2 in the denominator 3 times. C to the 4th to the negative 3rd power will now become c to the 4th to the positive 3rd power in the denominator. It's going to look like that. So time to start evaluating here. 5 cubed is 5 times 5 times 5. That is 125. 2 cubed, as we just talked about before, is 8. And c to the 4th, all that raised to the 3rd power, what happens is you get 3c to the 4ths multiplying, which means the 3 4s add, and that becomes c to the 12th. It's the same as taking the 4 and multiplying it by the 3 there. And that's actually your result. That's your answer. Positive exponents all the way. This fraction cannot reduce. There's no greatest common factor other than 1 for these guys, and so you're set. Now, another way to do this problem, and it's probably the only other way that I'll talk about, is that, I can apply the negative first prior to using the 3 at all. Let's say I want this to be all positive exponents to begin with, and just from the very beginning. What I could do instead is, this is a negative exponent as long as these are in these places. But what if I apply the negative to all these guys here and they move in those areas that I talked about before? These guys move down and this guy moves up. So what I could do is have them swap places immediately. Just take the reciprocal of the inside, just like this. And then just make sure that your exponent here is positive. So this is okay to do as well, and then that can get you right back here where we were before. So it doesn't matter which way you go about doing that first, whether you want to make this positive as long as you reciprocate everything, or if you want to keep it negative and then move them as you go, totally your call. Regardless, you're going to get this result, and that is your answer. Now, I was going to say you can double check your answer by plugging in a number into here, but that number is rather large. I'm going to avoid talking about that kind of thing right here and right now. Okay, let's write an explicit rule and a recursive rule for the sequence. Now, section 6.6 was on geometric sequences, but it refers to arithmetic sequences as well, and guess what? This one here is actually an arithmetic sequence. So, just to get a small talk on what these things are here, a geometric sequence is like an exponential equation, at least it has exponential growth, and then arithmetic is like a linear equation, or at least it has linear growth. Linear growth means that there's a common difference between your values here. Exponential, geometric, would mean that there was a common multiplier, a common ratio. This one happens to have a common difference. If you're unsure of what to add from here to here, you can always check and see what 8 minus negative 6 is. That's going to give you 14. That's 8 plus 6. 22 minus 8 is also 14. And 36 minus 22 is also 14. Now, we don't know how long the sequence goes. For all we know, it could end here or it could go on forever. But the fact of the matter is, for the three that they give us, there is a common difference. This is D. D is your common difference. The common difference is 14. Okay? So, now, part of what I'm talking about here, once again, this is an arithmetic sequence. Here's your general equation for an arithmetic sequence. And it looks a lot like y equals mx plus b. I have plenty of other videos that really do talk about this whole process. I just want to make sure you know the equation, to know what you're trying to attack. By the way, this is for an explicit equation for an arithmetic sequence. What it means is, to find the value, to find out what the value is, I got to use n, I got to use the term number right here in order to find out that value. And the way it explains it is with this. I'm going to be adding 14 every single time I want to jump to the next term. Plus 14, plus 14, plus 14. Now we want to make an equation that describes the number of times we add 14 to the term position that we're talking about. In other words, if I want to find the value of the first term, I want to be able to explain that I added 14 once to get that number. And to get to the second term, I want to say that I added 14 twice to get that number. Unfortunately, our addition right now is a little off. If I want to get the second number, it looks like I'm only adding 14 once. So let's make it add it twice. That means we would have had to have another number right here from the beginning that says, hey, the first term, let's add it once. The second term, let's add it twice. Third term, 3 times, etc. But that would mean we would need this number here as well. So this is when n equals 1, so this is a sub 1, here's a sub 2 and a sub 3. We need a sub 0. What is the value of the 0th term? So if I'm going to add 14 to get negative 6, I would have to subtract 14 this way to figure out what this term is. Negative 6 minus 14 is negative 20. So the 0th term here, a sub 0 is negative 20, and d, as we said before, is 14. You have all the information that you need in order to write in the explicit equation for this thing, and it looks like this. To find the value of any term n, you will take negative 20, and you will add 14 exactly n times. If I want to find the 100th term, I would do a sub 100. And I would do 14 times 100, which means adding 14 100 times, starting from negative 20. That would give you 1380. If you really want to know, the 100th term of this list is 1380. And one of the pros of the explicit formula is I can find the answer to very far away terms without having to do too much work at all. Just plug it into the equation and you're good to go. It's kind of nice. Okay, but that's for the explicit there. Let's look at the recursive. Let's get a different color. I tried green. There you go. Let's look at the recursive form, the recursive equation. And it looks like this. There are 2 different ways to write it, but I'll just go ahead and write it this way because I believe the book shows it like this. Remember that a sub n refers to the value of term number n, whichever. The third term, a sub 3 is 22, for example. The value of the third term is 22. So a sub n minus 1, in some case, that might mean something like a sub 3 minus 1, which is a sub 2. A sub 2 is 8, a sub 3 is 22. To find the value of the third term, 22, I'm going to have to take the value of the second term, 8, and add my common difference of 14. I know that sounded weird, but trust me, you say this probably more often than you think you know. For example, what if I asked you right here and right now, what is the value of the fifth term? Now, whether or not you know the answer is one thing, but whether you know how to do it is another thing. And I think all of you guys know what you got to do here. Take 36 and add 14. And that's going to give you 50. So the value of the fifth term is 50 because I took the value of the fourth term and I added 14 to it. That's what a recursive equation is saying. To find the value of the next term, you take the value of the current term, or the term before it, and add your common difference. The sixth term, I add 14 again. The seventh term, I add 14 again. That's what the recursive equation says. So in this case, your equation is just going to look like this. A sub n equals a sub n minus 1 plus 14. Now, there's one other bit of information that I'm going to include, and that is the value of the first term. Because if you're trying to ask somebody to write out a list of terms for you, and for every term, you got to add 14 from the previous term, that's okay, but you got to know where to start at. So we're going to start at the first term of -6, and we're going to keep adding 14 from there. So again, you know what recursive equations are. Maybe you don't know its name. Maybe you don't know its equation very well. And furthermore, it looks very weird. Maybe you're unsure of how to interpret this. However, you do recursive math more than you know. That's what I'm saying. If I ask you to find the value of the fifth term, it's unlikely you're saying, hang on, let me plug it into here. You know what I mean? I think you would know wisely enough to just add 14 again and take that, make it happen. Okay, next problem. Let's solve this exponential equation. It says 256 to the x plus 2 power equals 16 to the 3x minus 1 power. And the goal is to solve for x. It says, what value of x do I plug into here to make something plug into here? Okay, so the first thing that I'm going to do here is I'll just show you a different problem to begin with here. Let's say you had something like 6 to the x equals 6 to the 7th power. I'm not going to do too much with that. Basically asking, what does x have to be? Well, the end result here is that x is going to have to be 7, because 6 to some power equals 6 to the 7th. The only way these are equal is if this x is 7. I mean, I don't know how much to say other than that. That has to be true. You can almost ignore the bases. And that's the point. As long as the bases are equal to each other, then you can ignore them. In this case, the bases are not equal to each other, though. So we got to do something else. And really, what we have to do is we have to make the bases equal to each other. Okay, now that takes a little bit of work and understanding and knowledge of what's going on. Got to figure out somehow we can make these two match. Maybe you only have to manipulate one of the sides. I'm going to show you 3 different ways to manipulate sides. The first one will be probably the way you should do the problem. And then the other 2 are a little bit out there and different, but it depends on the problem, and maybe you're going to have to know how to do it. Okay. 256, if you didn't know, it is 16 squared. So if I rewrite 256 as 16 squared, wrap that sucker around parentheses, it's still raised to the x plus 2 power. This and this are the same thing. Now I'm not going to change this side. I'm going to leave it as 16 to the 3x minus 1 power. Okay, there's a property that we just talked about previously that said, hey, we got to make sure that this multiplies with these 2 things here. So this is going to become 16 to the 2 times x plus 2 power equals 16 to the 3x minus 1 power. Well, now just like this problem that you saw over here, now here we have matching bases. They both have 16. The only way for the left side to equal the right side now is if these exponents are the same thing. That means we can write a new equation founded upon that 2 times x plus 2 equals 3x minus 1. So the question is, what value of x do we need? If I distribute the 2 here, I get 2x plus 4 equals 3x minus 1. And solve regularly. How about I subtract the 3x over just to make this fun? Subtract the 4 over. I'll get negative x equals negative 5. Therefore, x equals 5. And that's your answer. Okay. Now then, I said that I would do this a couple different ways. So let's look at a second way. Let's say that I didn't want to change the 256 into something to match this side. Let's say I wanted to change the 16 into something to match this side. How can I change the 16 into 256? This one's going to get kind of weird, but I can do this. I can say that 256, the x plus 2, I can call 16 the square root of 256. Isn't that weird? The square root of 256 is 16, so I can rewrite it as that. Now this is being raised to the 3x minus 1 power. Now how does this help? Well, depending on how well versed you are with this stuff, a square root is the same as raising that value to the 1/2 power. So 256 to the 1/2, and off you go. Now this problem is starting to look a lot like the other one in the sense that I've matched bases, only now I'm going to have a 1/2. I need a 256. I'm going to need a 1/2 to multiply with 3x minus 1. So now the equation looks like x plus 2 equals 1/2 times 3x minus 1. You can distribute the 1/2. I don't know how much fun you'll have with it. Eventually you're going to get back to here. I could multiply both sides by 2, cancel out the 1/2, and I would be back right here. But I'm just showing you that you can take this idea as well, and it does work. It does. One final approach, and there are actually 2 different numbers that I'm thinking of with it, but maybe you didn't know that 16 was 256 was 16 squared. But maybe you knew enough about powers of 2 or powers of 4. Let's see how much you know about powers of 2. 256 is 2 to the 8th power. 16 is 2 to the 4th power. What I can do is I can change both bases if I have to. Both bases. So I can do this, where I get 2 to the 8 times x plus 2 equals 2 to the 4 times 3x minus 1. I would set these equal to each other. And then I would solve the rest of the way, and I'm still going to get the same answer. You can try these. I'm trying to save time by not doing that. Or, last one, 4 raises to these powers as well. 200, actually I don't know which one, 4 to the 4th. 256 is 4 to the 4th power. And, whoops, x plus 2. And 16 is 4 squared. So you can use any of these things. I'm just letting you know you can change both bases if you need to, have to, want to, find it more convenient, whatever it is. You can do that as well, and you are going to get the same answer no matter what you do, as long as you do the math right. So 4 times x plus 2 equals 2 times 3x minus 1, and eventually one more time you would get back to solving x equals 5. So a lot of different ventures. Because you asked the question, I felt compelled to answer a lot of different ways. Sometimes it's really useful and important, like what if this number isn't one of these numbers squared or cubed or something? What if it said 64 over here to the x plus 2, and over here it said that 16 to 3x minus 1? 16 to the 4th power isn't 64. You would have to change both of these bases to make this thing work. Do something in your favor. I know this is 4 cubed and 4 squared, or 2 to the 6th and 2 to the 4th. So there are ways to go about doing that with changing bases. It kind of works out really nicely, but make sure that the bases become the same thing. That's the important key to this problem here. Okay, awesome. Okay, let's graph f of x equals 2 times 6 to the x power. We'll compare that graph to g of x equals, this should say 6 to the x, excuse me. 6 to the x power, and then describe the domain and range of f. Okay, now I made a nice big set of axes here. I think it's going to work out pretty well for this problem. In order to do this problem, you have a lot of different options. I might start off with a table. I think at some point I need to let you know how to do it without a table, and you got to be able to follow along with that pretty well. I'll choose some negative, some positive, and we'll see what comes out here. So I'm going to do this twice. Oh, no, you know what? I'll just do it. I'll do it twice. The other time when I do the table, I might not be computing within the table as much. You'll see what I mean. So plug in x, get f of x. Plug in x, get g of x. Yada, yada. Let's choose some negative, some positive. And whatever we can fit on our graph, we'll try and do our best. Okay, when you do 2 times 6 to the x power, I want you to know you cannot do 2 times 6 to begin with. You can't change it to 12 to the x. Order of operations says you have to do 6 to the x first. So no matter what I do here, I got to make sure I raise this to some power, and then I double it. So 6 to the x power, 6 to the first power is 6. If I double that, I get 12. 6 squared is 36. If I double that, I get 72. You can already see how large this is getting. 6 cubed is 216. If I double that, I get 432. Now, you might not pick up on this pattern very much, but if you know anything about exponentiation, you probably realize I'm multiplying this number by 6 each time. Which does mean if I'm multiplying all these by 6, then I'm dividing by 6 going this way. 12 divided by 6 is 2. Let's see if that lines up with what we know about a 0 power. 6 to the 0 power is 1. You double that, you get 2. Okay? Divide by 6 again. How do negative exponents work? It's how many times you divide by 6 here. We're going to divide by 6 once. 2 divided by 6 is 1/3. So we're going to get 1/3 there. Now if I said divide by 6 again, this is going to get kind of weird. So 1/3 divided by 6, what is that? Well, you can also just as easily multiply by 1/6. Technically, that's what's happening. Multiply by 1/6, we get 1/18. Now remember, this is already becoming doubled of what it was before. First I'm doing 6 to the negative second power, which is, by the way, 1 over 6 squared, which is 1 over 36. And then you're multiplying that by 2. That becomes 2 over 36, which becomes 1 over 18. Multiply by 1/6 again, and you get, I don't know, 1 over 108, I think. So we get that again. Anyway, I'm not going to be able to fit all these points here, really just a couple of them. When they say graph this thing, man, there's not much room for this, at least not on a practical scale. And any curve thing I draw is not going to look good, so I pre-apologize for what I'm about to do here. But I have the points 0, 2, and 112 that I can totally fit on here. 0, 2, and 1, 12. And then I have negative 1, 1/3, like that, and negative 2, 1/18, and it goes down so sharp, so fast. Remember, this goes all the way up to 2, 72. I barely even get halfway there with the 36 right there. So it doesn't even pass this part of this line even close to here. So I'm going to draw a line there. It's not a realistic thing to do, but I won't be able to get a good looking drawing otherwise. So I'm going to kind of get like a little bit of like a straight down right there. It shouldn't ever be straight, but just to get it the best look possible, because you see how I draw this part here? Does not look good. I shouldn't have to go that far up, but I want to for the 6 to the x graph here. Anyway, technically it's curving there the whole time. And it curves down here, and it never actually crosses or touches the x-axis, despite what it looks like I was doing. Because I can raise 6 to negative infinity, and that's still 1 divided by 6 to the infinity, which is still a number greater than 0. So there's a nice little asymptote there. That's just a horizontal line that says, well, it keeps going closer and closer, but never quite reaches. Let me draw an arrow on this side where my straight part of my line is right there. Okay, there's that graph. Now, the other graph right here, technically I probably should have done it first. I don't think they're asking you to really graph this next one, but they're asking you to compare the graphs. And you might not be able to tell too much with the graphs alone, but you might be able to tell with just the tables here. Do you remember how I got these values? I did 6 to the first power and then I doubled it. What if I didn't double it? I would get just 6. And 6 squared was 36. It's just going to be half of what these numbers are. The reason why I'm writing this in a table is to show you that effect. 6 to the 0 is 1. Here's 1 over 6 to the first, or 1 over 6, 1 over 36, and 1 over 216. So I'll try and graph this a little bit here, but just keep in mind what's actually going on here. Every number here is exactly half the number of this number, these numbers here. Now you're saying, no, look, this is 36 and this is 18. No, this is 1 over 36. 1 over 36 is half of 1 over 18 because the denominator is doubled. All these numbers are half of the heights of these. Otherwise, these graphs are the same. So clearly, what's changing here? This 2 is affecting everything because it's doubling every number we get from here. So that's what's going on. So if you did see the graph, it would look like this. 0, 1, 1, 6, and all the way up to 2, 36, which is why I wanted to fit this here. It's not going to look that great, and you won't be able to see the comparison as well as I'll be able to, but then there's 1 over 6, and there's 1 over whatever else, and it's going to approach down here just like this, but it's always going to be half the height of the other guy at any x value that you're looking at. Sorry about these graphs, y'all. You gotta know how to draw exponential graphs. This is not gonna look good. Whatever. Look, it's 1234. Ooh, nice time. But it's 1234. All right, that I didn't anticipate it was just gonna look that bad. When you make these slides to begin with, you start to say like, hey, these are gonna look okay, and then suddenly you're like, ugh, what's going on? Anyway, there's that. Now it says describe the domain and range. And I know we haven't done much on domain and range, but the real question, the real thing it's asking is, tell me how far left and how far right these graphs can go. Could I plug in any value of x and always get a value of y? The answer is yes, you could. So the domain of both of these things is all real numbers. It means that you can plug in any value for x and always get a value out for y. The range is a different story. The range asks, based on the values of x you can plug in, how far up and down does your graph go? Well, it goes up forever. Both of these do. So definitely goes up forever. But that asymptote feature says that we're always going to be above y equals 0. We're always going to be a positive value. These values can never be 0. These values can never be negative. So the range would say only positive y values. Y can only be greater than 0. Now, I don't think those kind of questions on your final for domain and range, but you got to know what domain and range are. It's just one of those things. You got to know. Okay, that was the chapter 6 stuff. Now let's look at chapter 7 stuff. Factoring polynomials completely. Okay, so let's factor this completely. To kind of save time, I'm just going to factor straight up here. We have a cubic with no common factors for everything. But if we pair these off, if we pair off these two and these two, you will get some common factors. H cubed and 2h squared both have common factors of h squared. If I factor h squared out of h cubed, I'm left with h. If I factor h squared out of 2h squared, I'm left with 2. And then here you can factor, it looks like a 9 out of both of these, but I actually want to factor out a negative 9. And the main reason is because I want this inside result to become a positive h and a positive 2. I want this quantity to match with this quantity here. Ultimately, what you're looking at is a common factor set in both big term guys right here. I can factor out the h plus 2 from both terms. And when I factor h plus 2 out from here, I have that negative 9. When I factor the h plus 2 out from here, I have the h squared. And now I have factored by grouping. And that's all good and great. There we go. That's a good start. Okay. Now I want to emphasize the word start there because this is still a factorable quadratic. I'm going to tell you, this is a difference of two squares. This is h plus 3 times h minus 3. Maybe, I will show you a little bit more on that later. But seriously, I'm at the point in the year, the end of the year, where it's something that maybe you don't know how to do it immediately, but as I do it, you should be able to recognize what it is that I just did instead of saying, wait, where did the 3's come from? Why is 1 a plus and why is 1 a minus? If you can't recognize it at this point, I mean, that's something that says something about how you've been paying attention to me all year, or doing practice with these all year, or studying your notes, or anything like that. So I do have a whole factoring video on this stuff for you. I do want to do these problems. Know what I mean? Anyway, this factors out completely there. Same with the factoring by grouping. A lot of people say, well, wait, how did you only get one of these here? Because I factored it out. Notice what happens here. I do want to show you this. Notice what happens if I wanted to distribute this. I could take the h squared and I could multiply it with h plus 2, and I could take the negative 9 and multiply it with h plus 2. I'm distributing each term in one quantity to the quantity in itself. I'm multiplying h squared by this thing, and I'm multiplying negative 9 by this thing. See, this matches with this right here. They're both the same thing. Factoring is the opposite of distribution, so if I can distribute to go this way, then clearly I can factor to go that way. And this is a difference of two squares. This is what it factors down to right there. That is your result. If you ever want to double check, try and multiply it all back together. You should get that again. Okay, solving polynomial equations in factored form. The first guy right here, what we got to do is factor this thing out. It is set equal to 0. So if we factor it into a product, then we can use the zero product property. So let's get to it. We've got to find out what two numbers multiply to become 49 and add to become 14. And the answers are 7 and 7. So d plus 7 times d plus 7 equals 0. The zero product property states if these two numbers multiply, if this multiplies with this to become 0, one of these has to be 0. Now look, the bottom line is both of these say d plus 7. So eventually you kind of just say, all right, d plus 7 has to equal 0. Therefore, d is negative 7. If you ever want to double check your answers, take your solution and plug it in to there for d. You'll get negative 7 quantity squared plus 14 times negative 7 plus 49 equals 0. This is 49. This is negative 98. This becomes negative 49, and this becomes positive 49. And 0 equals 0. Okay, that checks out. Good. So there's zero product property, there's double checking. Now I factored it by asking what two numbers multiply to this and add to this. What you could also do is connect the fact that it's a quadratic, so clearly this is something squared, it's d squared, and 49 is also 7 squared. And then you can ask, is the middle term the product, double the product of d and 7? Yeah, 14d is 2 times 7d. 7d, not 70. So it's a perfect square trinomial. It's this guy squared, it's this guy squared, and it's double the product of 7 and d. Awesome. So if you know that this works out to be d plus 7 quantity squared right off the bat, you can jump straight into there as well. This one, it doesn't matter as much. In other problems, I think you'll appreciate that. But d equals 7, there's your answer. Negative 7, excuse me. All right, next problem. 6x to the 4th plus 8x squared equals 26x cubed. Now, I know why this was asked about. It's a pretty challenging problem, all told. This problem was in standard form. I think it was good to get it in standard form to start off. So let's move that 26x cubed on over. We'll get 6x to the 4th minus 26x cubed plus 8x squared equals 0. Now you're still like, well, you're not helping me much. How does this help me solve? It's not even a quadratic. Yeah, you're right, it's not a quadratic. But these all have x squareds as factors. So I can factor x squared out of every term here and be left with something inside there. And I can also factor out a 2 I can factor out a 2x squared from here, and now I have a 3x squared inside here. I have a negative 13x inside here, and I have a plus 4 right there. So now what you have is a product. You have 2x squared times this equals 0, which you can do zero product property from here and say that either 2x squared equals 0, and if it does, divide both sides by 2, you get x squared equals 0. Take the square root of both sides, you get x equals 0. That's one solution. Or this whole thing equals 0, and now it's almost like doing a problem like the previous one where you just got to solve it like a quadratic. Now the difference between this quadratic and this quadratic is this does not have an a value of 1. It has an a value of 3. That means when we factor, we don't just ask what two numbers multiply to 4 and add to 3. We ask what two numbers multiply to 3 times 4, 12, and add to become negative 13. I think I said 3 before I meant negative 13. Those two numbers are negative 12 and negative 1. So what I'm going to do with this now is I'm going to do factoring by grouping by rewriting this expression to be 3x squared minus 12x minus 1x plus 4 equals 0. And I continue to solve. Factor by grouping like we just did before. And I can factor a 3x out of these two terms. I get x minus 4. And remember, I want to factor out the right thing so that I can get x minus 4 in here. It looks like I got to factor out a negative 1, and I'm left with an x minus 4 inside there. The x minus 4s can factor out of both terms, and I'll be left with a 3x and a negative 1. That's how this thing factors. I went from here all the way down to here. Now I can mentally do it. So maybe some of you guys can as well, I'm not sure. Otherwise, factoring by grouping was really the way that we've been doing it this whole time. But we're not finished with the problem. We still have to do zero product property. Either 3x minus 1 equals 0 or x minus 4 equals 0. If x minus 4 equals 0, then x equals 4. That's my second solution. Remember, our first solution was this one. Next one, add 1 over, we get 3x equals 1. Divide by 3, you get x equals 1/3. So we have 3 solutions here. Now you're like, why do we have 3 solutions? I thought it was a quadratic. No, the first problem was a quartic. It was actually 4th degree. So you could have as many as 4 solutions. Remember, technically 2 of your solutions are x equals 0 because this was an x squared. It's like x times x. So this has a multiplicity of 2. But these are your 3 different answers here. You could try and plug them in. I think the 1/3 will be a little overbearing, plus the quartics and stuff. I think you're going to have to trust your answer at that point. But there are solutions. It's factorable, and that's what it ends up being. You know, one thing you don't want to do right here is you do not want to divide by x squared. Notice that I factored the x squared out. If you want to divide by 2, that's fine because 2 is a constant value. Don't divide by these, though, and cancel out those parts because then you'll lose your solutions. Do not do this because you'll lose this solution of 0. You have to factor it out, which is like dividing, but you didn't lose anything when you do that. Okay, got 2 word problems for you here. You're jumping on a trampoline. For one jump, your height of y in feet above the trampoline after t seconds can be represented by this equation. Let me rewrite it all in one line here. How many seconds are you in the air? Okay. Y is the number of feet above the trampoline. And if you're jumping on the trampoline, that means that when y equals 0, then you're on the trampoline. So what I can do is I can set y equal to 0. I'm going to change this into a 0. Say negative 16t squared plus 24t equals 0. Because if I solve for t, what I may get is more than one t value. Remember, it's a quadratic. You can get possibly 2 answers. So I'd like to get more than one t value here, because what's that going to do? It's going to tell me the time between when I left the trampoline and when I went back on the trampoline. So say I get a time of 3 seconds and 10 seconds. And that means that I left the trampoline 3 seconds in, and I landed on the trampoline 10 seconds in, which means I had a 7-second jump. or I was in the air for 7 seconds, which is a long time. It's clearly not realistic. I'm trying to not say the actual answers. But the point is, set y equal to 0 and solve for t. That can help you explain it. And the word problem really helps out with that. So, okay, this has a common factor of t. And a common factor looks like of -8. I like to factor out the -8 in this case here. -8t is factored out, and I'm left with a 2t here and -3 right there. This is factored form. This way I can use zero product property. So in zero product property, either -8t equals 0, divide by -8, you get t equals 0. That's one value. Or 2t minus 3 equals 0. So 2t equals 3, and t equals 3 over 2, which is also 1.5. And normally I wouldn't tell you to do a decimal, but they're asking us how many seconds are you in the air. Now, it looks like I leave the trampoline 0 seconds in. It looks like I land on the trampoline 1.5 seconds later. So it looks like you are in the air for 1.5 seconds. That's how it works. Now, one other thing I want to say about this, I know it's not a part of the problem really, but I want to show you what this graph kind of looks like and what it means. If we get these two values, they're like our t-intercepts. T is kind of like x this time. Here's t, here's y. There are two t-intercept values at t equals 0 and at t equals 1.5. This is a negative quadratic equation. That means this is an upside down parabola. This is the model for you going in the air, and obviously the parabola goes back down, but this is when you hit the trampoline again. So you go up, you hit a high point, and then you come back down. So that's what that thing looks like. This is at 1.5 comma 0. This is at 0 comma 0. And that's the model for this parabola. Pretty nice. I like it. Okay. A cardboard box in the shape of a rectangular prism has the dimensions shown. And they show you the image and the breakdown. Write a polynomial that represents the volume of the box. Okay. This is supposed to represent like length, width, and height. And if you know the volume of a box is length times width times height. Now, they don't just mean that. They mean give me a polynomial equation. They mean use these expressions here, but not just that. In fact, I think I need more room for this problem, really, to be honest. So I'm going to do all number 1 down here. Okay, here's number 1. Number 1's going to be in purple, or whatever that is. Number 2 is going to be that color. So the volume, which we don't know what the volume is, but we know how we can express it. X plus 6 times x minus 2 times x minus 1. Those three factors here are what represent the volume. And we can now write a polynomial based on it. You might say, here's a polynomial. Yeah, but I think they mean write it in standard form. This is in factored form, and I'd like to get standard form out. So we got to multiply. Oh, hang on. I'm going to go back for a moment. I said that this is what we are going to cover. We're also covering multiplying binomials, adding and subtracting polynomials. Oh, you know what? This isn't a binomial. Oh, well, yeah, it is. And writing a polynomial in standard form. All right, there are a few more things that are going to be covered here. I forgot that this is how it's going to appear. All right, so we got to multiply these things out. Now, it's best that you multiply any two at a time. So I'm going to multiply these two together first. Distribute. X times x is x squared. Then minus 2x plus 6x, that's plus 4x. And then minus 12. Boom. Now we got to multiply that all by x minus 1. Now we got to, kind of distribute this thing out. Get it back in this purple again. X squared times x is x cubed. X squared times negative 1 is negative x squared. 4x times x is 4x squared. 4x times negative 1 is minus 4x. And then we got the negative 12 multiplying with x, and the negative 12 multiplying with negative 1. That's a plus 12. So this is what volume equals. I can combine some like terms now. Negative x squared plus 4x squared is 3x squared. Negative 4x minus 12x is negative 16x. And then we have the plus 12 right here. Okay. So then they say the volume of the box is 60 cubic inches. What are the length, width, and height of the box? So this is the polynomial. Now we got to go on to that second question there and say the volume of the box is 60. Now we know that V equals 60. So we're now going to substitute 60 for V right here. 60 equals x cubed plus 3x squared minus 16x plus 12. And we got to solve. So as you can tell, this looks like one of those cubic, factoring by grouping things, but you can't or don't want to factor by grouping until this side equals 0. So if I subtract 60 with everything here, I'm going to do 12 minus 60, and I'll get x cubed plus 3x squared minus 16x minus 48 equals 0. Now I can't do a zero product property thing until I get this factored down. By the way, you can't use quadratic formula on this thing because it's not a quadratic, it's a cubic. Plus, we're not in that chapter yet. So don't do it yet. You can factor an x squared. You can factor an x squared out of here, and we're going to get x plus 3. And then you can factor a negative 16 out of here, and you can get x plus 3 again. Okay? This, factor the x plus 3's out of both terms, you'll get x squared minus 16. Okay? And this is a difference of two squares that factors the x plus 4 times x minus 4. Now I'm going to show you a second way you can do this part here, because this isn't just a factoring problem, it is a solving problem. And here's your x plus 3 equals 0. So zero product property states that if these three things equal 0, either this one equals 0, or this one equals 0, or this one equals 0. Now, this isn't, well, actually here, before I talk about that, let's look at this thing right here. If I did zero product property right here, I could say that either x plus 3 equals 0 or x squared minus 16 equals 0. And without factoring it, I could add the 16 over and take the square root of both sides. Guess what you'd get? Plus or minus 4. Notice how those two answers show up right here. Now, this problem didn't ask us to solve for x. The problem asked you to find the length, width, and height of the box. Now, x is just part of the expression that represents these values right here. It's a part of it. And there is more than one x value that we found, a negative 4, a 4, and a negative 3. Now, the thing about this problem, though, is that if you try and plug in some of the different x's into some of these, like if I plug negative 4 in, let's see what happens. Negative 4 plus 6 is 2. Negative 4 minus 2 is negative 6. You can't have a distance that's negative, so the negative 4 won't work. The negative 3 also won't work, and let's hope that the 4 works, though, so let's try that. Let's try 4 plus 6, which is 10. 4 minus 2, which is 2, and 4 minus 1, which is 3. 10 times 2 times 3 looks to be 60. And all these lengths are positive. So it looks like our length is 10, our width is 2, and our height is 3. And those are your answers there. That is the final response with units. So you notice, excuse me. So you notice how I was doing that. I took x and I solved for those things, right? This was 4 plus 6. This was 4 minus 2, and this was 4 minus 1. That was the length, width, and height of the box. It's kind of a long problem, but you can get there. You can get there. Okay, chapter 9 stuff. Now I have 5 problems that are the exact same instructions but different problem types here. I'm going to see how much I can do with these, but this is what's going to take up most of the time, the last 10 problems of this thing. Solve the following by factoring, graphing using squares, completing the square, or the quadratic formula. I'm going to try and do as many as I'm able to do. Let's start with factoring, with the letter F, factoring. Okay, what two numbers multiply to 3 and add to 4? 3 and 1. Zero product property allows us to say either x plus 3 equals 0, so x equals negative 3, or x plus 1 equals 0, so x equals negative 1. That's it. Let's try completing the square. So completing the square here, what I'm going to do is I'm going to move that 3 over to the other side. I'm going to subtract it. Then I'm going to complete the square here by adding in a certain number that gives me a perfect square trinomial. You find this number by dividing the linear term by 2, which is 2, and then squaring it, which is 4. So if I add 4 to this side, I'm going to have to add 4 to this side. It's a balance thing. Okay, this is going to factor down into x plus 2 quantity squared. It's the answer to the question, what two numbers multiply to 4 and add to 4? It's going to be 2 and 2. However, it's always also this number right here that gives you it. You'll be wise to remember that, especially when there are fraction issues and stuff like that. Unless it's, really big numbers, Negative 3 plus 4 is 1. So technically, anytime you solve by completing the square, you also solve by using square roots, because I'm about to take the square root of both sides now. This becomes x plus 2, and this becomes plus or minus. The square root of 1 is 1, so plus or minus 1. So I subtract the 2 over, I get x equals negative 2 plus or minus 1. Now I don't want to leave the answer like that, I want to split that. X can either equal negative 2 plus 1, or x can equal negative 2 minus 1. Negative 2 plus 1 is negative 1, negative 2 minus 1 is negative 3. So I got the same answers here using completing the square as I did by factoring over here. Then there's the quadratic formula. This is in standard form, so a is 1, b is 4, and c is 3. And in the quadratic formula, I like to try and evaluate the discriminant first by doing b squared minus 4ac. b squared minus 4ac is going to give us 16 minus 12, which is 4. Inside the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac, right there, all over 2a. So x equals negative 4 plus or minus 2, all divided by 2. So x will either equal negative 4 plus 2 divided by 2, or x will equal negative 4 minus 2 divided by 2. So over here, x will equal negative 2 over 2, which is negative 1, or x will equal negative 6 over 2, which is negative 3. As you can tell, I can't spend a lot of time teaching these problems here for the very reason that otherwise it's going to be a time issue. But I'm going to be doing this more than one time, so if you kind of follow along with what I'm doing here, I hope it's going to connect pretty well. The last couple ways I'm going to look at this problem is with the graphing. And I want to be able to do this because I know that graphing doesn't really appear on this test at all with the quadratic, so I got to make sure I do it at some point. So let's graph. Oops, same color. Let's go ahead and graph. Now, in order to graph this thing, we either got to use a table or get it into vertex form, yada yada. No matter which way you do it here, and this is going to be a very, very rough sketch graph, but if I make a table, I want to find the vertex first. I can find the vertex's x value by doing negative b over 2a. That's negative 4 over 2 times 1, which is negative 4 over 2, which is negative 2. So the x value of the vertex is negative 2. the y value, and when I say y value, I'm referring to this equation. I'm plugging y in for 0, because if we graph this and we find out what the values of x are when y equals 0 at the x-intercepts, then we'll get the solutions. So I'm going to do y equals negative 2 squared plus 4 times negative 2 plus 3. And that's going to be 4 minus 8 plus 3, which is negative 4 plus 3, which is negative 1. So your x value is negative 2, your y value is negative 1 of your vertex. Okay? Now let's go and graph that. That's at negative 2, negative 1. And you can build a table around that x value. So I'm going to do that pretty briefly here. Get x and y. So let's plug in, here's negative 2, we can get negative 3, negative 4, get negative 1 and 0, 1 if we're lucky. I probably won't use that. I won't. So I have negative 2, negative 1 as my vertex. Now let's try and plug in something like negative 1 into the equation. We'll get 1 minus 4, which is negative 3, plus 3, which is 0. If this is 0 reflecting across the vertex, this will also be 0. Okay, so this this matches our answers that we got before here. Negative 3, 0, and negative 1, 0 seem to match everything that we've been getting here before. Negative 3, negative 1, negative 3, negative 1, negative 3, negative 1. So that would be solving by graphing. I'll finish this though. If I plug in 0, 0 plus 0 plus 3 is 3. If this is 3, that's 3. So there are two other points on this graph here that look like this and that. And there's your parabola. Very terrible looking. But it's the U shape and it crosses at negative 3 and negative 1. You can also get into vertex form with this thing here by taking your equation, y equals x squared plus 4x plus 3, and completing the square on this, but keeping the y equals along the way, and just writing out that vertex form. So I'm going to move the 3 out of the way, and it's going to be the same thing that we used to complete the square here. Divide by 2, square it, you'll get a 4. But now I'm going to subtract 4 over here, because I'm on the same side of the equation. I got to add 4 to make it 4 bigger, subtract 4 to make it even back to where it was before. This portion factors down. This portion factors down to x plus 2 quantity squared, and 3 minus 4 is negative 1. So this is your vertex form. What it does is it reveals your vertex. Here's what the vertex form actually looks like. A times h, x minus h quantity squared plus k, where the vertex is at h comma k. So this says x minus h, this says x plus 2. The only way that could happen is if you're subtracting a negative 2. That means your vertex is at negative 2 comma plus k minus 1, negative 1. So there's your vertex. You can now use that up here, and actually this would be easier with a table. Vertex form is easier to work on with a table if you build around that vertex. The numbers are easier to compute, really. And there's your result. So that's all of that problem. I used every method that I actually possibly could, and I probably won't do the graphing ones much more. I don't even know if the other problems will set up for me to do it as well, but I wanted to do that one just in case. Okay. All right, solve this one. 4b squared plus 8b plus 7 equals 4. Okay, this one gets a little stranger. Let's subtract the 4 over to the left side. 4b squared plus 8b plus 3 equals 0. First of all, acknowledge the fact that no common term, no GCF, no greatest common factor. So you got to stick with what you have here. So if I solve by factoring, I got to figure out what two numbers multiply to 4 times 3 and add to 8. So what two numbers multiply to 12 and add to 8? They'll be, I just had it, 6 and 2. They'll be 6 and 2. Once again, 6 and 2. So as far as factoring goes, I'm going to rewrite 8b into 6b plus 2b. So I can now factor by grouping. Group, group, and let's factor out a 2b from here to be left with 2b plus 3. Take a look, this is already 2b plus 3, so what do? You got to factor out a 1. That can leave you with 2b plus 3 here still. 2b plus 3 is going to factor out of both of these here, and you'll be left with 2b plus 1 over here. This all equals 0. I can now use this to solve. Now notice I never attempted to factor this beginning one because it wasn't set equal to 0. When I'm set equal to 0, then I can use 0 product property, which I'm about to do right now. Let me keep the same color here. Either 2b plus 1 equals 0 or 2b plus 3 equals 0. So let's solve for what b would have to be then. 2b can equal negative 1, so b can equal negative 1/2. Or 2b can equal negative 3, so b can equal negative 3/2. And those are your two answers right there. Okay, the next one I'm going to do is completing the square, and I'm going to say it with a little bit of hesitance here because I'm sure you don't know really that much about what to do when this thing is a different kind of number. First of all, I got to move this 3 over to the other side. Equals negative 3. Okay, here's the thing. You cannot have a 4 in front of here. I have to factor the 4 out. B squared plus 2b. Inside here, I'm actually going to complete the square. Now, whatever I do on one side, I have to do to the other. But because 4 is multiplying by whatever item's inside here, that means 4 also has to multiply by whatever item is going over here. So if I divide 2 by 2 and square it, I get 1. So this 4 is going to have to multiply by this 1 right here. That way I can keep the equation balanced. This factors down into b plus 1 quantity squared, and negative 3 plus 4 is a positive 1. I want to divide both sides by 4 because I want to start to get b by itself now. Divide by 4, divide by 4. I'm going to get b plus 1 squared equals 1/4. Now I can take the square root of both sides. So now I'm going to get b plus 1 equals, first of all, plus or minus. The square root of 1/4 is the square root of 1 over the square root of 4. Okay, so now I can subtract 1 over, and I'll get b equals negative 1 plus or minus 1/2, which means b either equals negative 1 plus 1/2. Whoops, not plus or minus. b is negative 1 plus 1/2, or b is negative 1 minus 1/2. This is negative 2 over 2 plus 1 over 2, which is negative 1 over 2. And this is negative 2 over 2 minus 1 over 2, which is negative 3 over 2. And there are your results that match those ones right there. And I'm only showing you it so you're just very well aware of it. I want to do completing the square as often as I can or feel like I should. Because this became an integer, I was fine doing that one with you. I don't think I want to do completing the square on too many that give me fractions, fractions in here. I might end up doing 1 or 2 because I want to match and show you that the quadratic formula answer is the same. Speaking of which, I'm going to do quadratic formula on this thing right now. First, by evaluating the discriminant. Now, a equals 4, b equals 8, and c equals 3. You know, you got to use the standard form equation if you're going to do quadratic formula. So I got to use this one. Then I can solve for b that way. Start with the discriminant. We're going to do b squared minus 4ac, which is 64 minus, 64 minus 16 is 48, which equals 16. So when I do quadratic formula, I'll get b equals, and I'm saying b because this b here, not this b. Shoot, that's a problem when I say b here and b here. whatever, this b right there. B equals minus b plus or minus the square root of your discriminant, b squared minus 4ac, 16, all divided by 2a of 4. So b equals negative 8 plus or minus 4 all over 8. So it's either going to equal negative 8 plus 4 over 8, or it's going to equal negative 8 minus 4 over 8. This one here is negative 4 over 8, which is negative 1/2. This one here is negative 12 over 8, which reduces to negative 3/2. And there's your two answers there once again. Those are the three ways I'll do that problem there. Hey, you can do it however you need to, but now you see them. Okay, 2x squared minus 3x minus 15 equals 5. This is an example where I'm just going to do the factoring and quadratic formula, assuming that it's factorable here. So I'm going to subtract the 5 over, write it in standard form. 2x squared minus 3x minus 20 equals 0. And you know what? This time I'm going to play some mental factoring with you, and then we'll do the factor by distribution. Because this is a 2 and a prime number, and it's not a common factor, that means that I know that 2x and x are going to appear in this thing right here. 2x and x, boom. Now I'm going to insert some values here, multiples of 20, like 10 and 2, 20 and 1, 4 and 5, 1 negative, 1 positive, until I get them to multiply to a sum of negative 3 if I were to FOIL. Let's try this for example. You'll kind of see what I mean here. Let's try plus 4 minus 5. When you FOIL this out, it would say 2x squared minus 10x plus 4x minus 20 equals 0. And negative 10x plus 4x is negative 6x. It's not negative 3x. That means these are not the factors of this thing. So I got the wrong set. Now I can try again, and this time when I try, maybe I'd try and switch the 4 and the 5 in a different way. How about negative 4 here and positive 5 here, something like that. And we'll get 2x, oh my god, yep, this thing works. Oh, good. Didn't even mean to. 2x times negative 4 is negative 8x. 5 times x is 5x. Negative 8x plus 5x is negative 3x. So there. If you want to do it I don't want to call it the normal way, but if you want to do factoring by grouping, you find what two numbers multiply to become 2 times negative 20 and add to become negative 3. That'll be a negative 8 and a positive 5. So when you factor by grouping, it'll say 2x squared minus 8x plus 5x minus 20 equals 0. Factor by grouping, you'll get 2x times x minus 4 plus, whoops, I just did what my students do, plus 5, factor the 5 out times x minus 4. Factor the x minus 4s out, and you get this thing right there. And then you're left with a 2x and a 5 right there. And that's what it factors down to. Cool beans, right? So either 2x plus 5 equals 0, or x minus 4 equals 0. If 2x plus 5, well here, if x minus 4 equals 0, x equals 4. If 2x plus 5 equals 0, subtract 5, divide by 2. Negative 5/2. And those are your two answers. Let's see if we can get the same answers there using the quadratic formula. Let's use the dark green. I bet you can't even tell that's green. I don't know. It barely looks green on my screen. It pretty much looks black against the white screen. All right. Let's do the discriminant first. Here's my standard form. You know that a is 2, b is negative 3, c is negative 20. Let's do b squared minus 4ac. That'll give me 9 minus 8 times negative 20. That is positive 160, which is 169. Now 169 is a perfect square value. It is actually the perfect square of 13. So when I do negative b plus or minus the square root of b squared minus 4ac all over 2a, I will be getting plus or minus 13 right here, all over 4. So here we go. X can either equal 3 plus 13 over 4, which is 16 over 4, which is 4, or I can get 3 minus 13 over 4, which is negative 10 over 4, which reduces to negative 5 over 2. And there are my two answers right there. Now I'm not going to solve this one by completing the square, because if I factor 2 out, I'll be left with a fraction here. It's just not worth the time or hassle. If it's something, I'm not here to impress you guys with this stuff. It's something that if you're not expected to do for your test, I'm not going to bother with it. So these are the only two conventional ways I would do that one problem there. Okay, this one looks a little big, but I promise that, if you clean things up and put them in standard form, it's not that bad. So let me start with standard form here. Otherwise, it does look kind of bad. It looks a little weird. I'm going to get the quadratics and stuff first so I know exactly where everything's at. Okay, awesome. Okay, I'm going to try and move everything to the right side. I'm going to add 3k squared. I'm going to add 2k. I'm going to add 6. I'm going to add 3k squared. I'm going to add 2k. I'm going to add 6. These cancel completely. On the left side, you're left with 0. Excuse me, on the right side, you're left with 0. On the left side, you're left with a 4k squared. Looks like these cancel here, and then a negative 25. Okay. Let's solve by factoring first. Now, if you're going to solve by factoring, you got to ask what two numbers multiply to 4 times negative 25 and add to what? Well, there's a term missing in the middle, and it would be a 0x. So you'd be asking what two numbers multiply to 100 and add to 0. And the answer is positive 10 and negative 10. So when you factor by grouping, you get 4x squared plus 10x minus 10x minus 25 equals 0. You factor a 2x out of both. Again, greatest common factor, please, every single time. You'll be left with 2x plus 5. Factor out a minus 2x over here, or excuse me, a minus 2. Minus 2. Oh, jeez. Pardon me, it's late, minus 2, you're left with 2x. No, not minus 2. See, it is late. Negative 5. Factor out negative 5, you're left with 2x. I'm like, 2x times that, isn't that? 2x plus 5, that equals 0. Factor out the 2x plus 5s, you're left with 2x minus 5. Now, before I move on with zero product property there, let's look at this thing again, but without all that stuff that I just wrote right here. What if instead I took my dude right here and I realized something about this? Hey, it's a quadratic equation, which means this is a squared product. 25 is also a perfect square of the number 5, and there's no middle term, and they're separated by subtraction. This is called a difference of two squares. If you notice it from the onset, you can say, hey, this is 2x squared, and this is 5 squared. And if you know that a squared minus b squared is a plus b times a minus b, then you're in good shape, and you got the exact same thing here in, you don't even have to write this step. You got the exact same thing here in one step, or two at the most, as you did in several steps here that involves factoring by grouping, possibly making mistakes like I kind of did, and the rap sheet. But we're still not done. Either 2x plus 5 equals 0, or 2x minus 5 equals 0. So 2x equals negative 5 and x equals negative 5 halves. Or 2x equals 5 and x equals 5 halves. And those are the two answers. They're opposite versions of each other. Kind of sweet. That's the factoring method. Let's try another one. Starting from standard form here. Let's try the square root method. We haven't seen that one yet. Now, how come I can use the square root method here? Because I don't have an x term. That means I can isolate my x squared value. This says 4x squared minus 25 equals 0. Instead of factoring, I could add the 25 over, so I'm starting to isolate x. Now I can divide both sides by 4. I'll get x squared on this side, I'll get 25 over 4 on this side. And now I can take the square root of both sides. On the left side you'll get x, remember the absolute value of x, but I'll skip that step. And on the right side I have plus or minus the square root of 25 over the square root of 4. And there are your two answers right there. This is actually the fastest way to do this problem. Either or. Difference of two squares if you know that as well. But plus or minus 5 halves is the same thing as 5 halves or negative 5 halves. So I did it all kind of in just one fell swoop. And I can do that, again, because I don't have an x term. I can do the square root stuff. I couldn't have done it before without that. Okay, last one's quadratic formula. So my a value is 4. My b value is 0. See, there's nothing there. And my c value is negative 25. If I do the discriminant, it's going to be b squared, 0 squared, minus 4ac. Negative 4 times 4 is negative 16 times 25. Let's see, 16 quarters, that's $4, so 400. That's my discriminant. So x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Opposite of negative 0 is 0. We're just going to get plus or minus. The square root of 400 is 20. This is all over 8. Plus or minus 20 over 8. This can reduce. These can both divide by 4. 20 over 4 is 5. 8 over 4 is 2. Plus or minus 5 halves. So get the answer all three ways. Not going to graph this one, even though it is graphable. Well, here, I'll draw the quickest graph in the world. It's going to look like this. It's going to cross at negative 25, and that's at the vertex, 0, negative 25. It's going to go up sharply enough that it crosses here and here at negative 5 halves and positive 5 halves. Oh, whoops, negative 5 halves here, positive 5 halves there. That's the graph. That's showing what these answers say. It's like negative 2.5 and positive 2.5. Okay, I think this is the last quadratic one to solve for. So again, we're looking at doing standard form. Let's add this n squared over here. And we're going to get 9n squared plus 4n minus 16 equals 0. Unfortunately, there are no common factors. Also, unfortunately, it's not a perfect square trinomial. These are both perfect squares, but this is a negative, and this is not double the product of these two things here. Let's even see if it's factorable. Solve by factoring. If we do, we're going to say what two numbers multiply to become negative 16, excuse me, not negative 16, 9 times negative 16, that's negative 144, and adds to become 4. Okay, so we're going to test, I'm going to write these factors down because there are a lot of factors of 144. There's 1 in 144, 2 in 72, 3 and 48, 4 and 36, not 5, 6 and 24, not 7, yeah, not 7, 8 and 18, 9 and 16. No 10s, no 11s, 12 and 12. Negative product, positive sum, larger number is bigger. Smaller number is negative. Larger number is bigger, excuse me. Larger number is positive. Let's see if any of these ones add to 4 here. No, 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 no. No, that's 10. Nope, that is 7. Nope, that's 0. I listed all of the factors of this thing here. None of them added to 4. That means this is not factorable. That does not mean there's no solution. We don't know if there's a solution yet or not, but it is not factorable. That means you can't solve this by factoring. That means you have to find another method. Now this one I'm not going to do completing the square with. I cannot do the square root thing with, and graphing. There's absolutely no reason when it's not factorable either. So we have to use quadratic formula on this one. You could use completing the square when you're in Algebra 2. You're not going to want to. Let's use quadratic formula. So here we go. N equals negative b plus or minus the square root of, let's do that discriminant over here, b squared minus 4ac, which is 16 minus, oh boy, this is a big number, 144 times 4 is 576. Now, this is going to be minus a negative because this is negative here and I'm subtracting. So 16 plus 576, which is 592. Square root of 592 all divided by 2 times a is 9. 2 times 9. Okay. So this is a big problem. We have to see that this simplifies, and I know that it does at least a little bit. I don't know off the top of my head what the greatest common factor of this thing is, but I know that 592 can divide by 4 because 600 can divide by 4. 600, if 25 times 25, 75. So every 25 fours is 100. So 25, 50, 55, 60, 65. What am I saying? 25, 50, 75, 100. Duh, that's 400. 500 is 125, 600 is 150. So take away 2, that's 148. So root 592 does break down to root 4 and root, what did I say? 148? 148 breaks down to something else as well. Let's see. Root 4 is 2. Root 148 breaks down to a 4. You see, I can do another 4 here. A root 4 and a root 41, I think. So I guess this becomes 4 root 41 in the end. I guess, yeah. 40. I don't think that's 41. I think I'm miscounting something there. 4 and 41 clearly does not add up to that. 4, hang on a second. I'm sorry, because I'm doing this without a calculator right now. Oh, 20, not 40, 20, 30, 48, 37. There we go. That's better. So that becomes a 2. So 2 times 2 is 4. So 4 root 37. Okay, that was a lot of stuff there. So I simplified it. So n equals negative 4 plus or minus 4 root 37 all over 18. Now this is the weird part here because you would be done, but all of these, they can't divide by 4, but they can all reduce by 2, these fractions. So we'll get n equals negative 2 plus or minus 2 root 37 all over 9. And that's what this can ultimately reduce to. That would be your final answer based on that. Now I couldn't do any of that until I got this part out of the square root. Otherwise I wouldn't have been able to take care of anything there. So that'd be my result. That's probably one of the harder problems on this thing. Look, even for myself, you know, I mean, I'm doing it without a calculator, and it takes a while to do these things at times. you have to keep trying until it works. And, you know, some problems just get hard. There's one of them. That's one of them. Okay, I got some chapter 11 stuff, and then I'm done. And I'm checking out a little bit here because, you know, I don't want time to escape you as much as it's escaping me. Find the mean, median, mode of the data set. Okay, I'm going to find the mean. Well, I'll probably find the median first. I like to get my numbers in order before doing anything else, personally. That's me. I got a single digit number of 9 there. Now I see a 10, 2 10s actually. I see some 11s. 3 of them actually. 11, 11. By the way, I never did this yet. This is your take-home quiz. I haven't done it before, so I'm doing it right now. We'll see how we do. Here's a 12, 2 13s, a 14, and an 18. Oh, I see a 15. 2 13s, a 14, a 15, and an 18. Okay, and I've rewrote the list. Okay, I'll still do mean first just because it's on here. So the mean, calculating this thing, I'm going to have to add all these up and then divide by how many numbers there are, of which I never counted. So 4, 5, 6, whoops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So divide it all by 12. So that's going to be 19, 29, 40, 51, 62, 74. I better not mess this up. 74, 87, 100, 114, 129, 147. 147 over 12. Now I'm going to go to the calculator because I was saying I don't have one. I just meant I'm not using one. So here we go. Let's do 147 divided by 12. We're going to get 12.25. So the average value of this is 12.25. The median, it's a 12-number list. That means it's in the middle 2 numbers of this list. So these two, the 11 and the 12. The 11 and the 12 are in the middle. The median is calculated by averaging those 2 numbers. 11 plus 12 over 2 is 23 over 2, which is 11 and a half. Okay? Your mode is the number that occurs most frequently in the list, and I believe 11 appeared 3 times, and I think that's the one that would appear most as a result of that. So your mode's 11. Okay, now they ask you to make a dot plot of the data set, and a dot plot is just really having a number line, which clearly this is, having a number line, labeling it, and stacking dots on top of each other based on the frequency of the value's appearances. Now, the numbers range from 9 to 18, which means as long as I can fit those values in on here, I'm pretty good. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16, 17, 18, 19, 20, 21, 22. Yeah, so I'm clearly, look, there are a lot of numbers here. There are too many almost. So I'm just going to start it here. 7, 8, 9. Sorry about this. I guess you had to do the same. I really should have started at 0. Let's do that. Why not? Why not? All right, let's start this thing at 0. Very nice. Okay, make a dot plot. Okay, so there's a 9. Now look, having this in order helps this as well. There's a 9. There are 2 10s. And try and get the heights kind of the same when you do. Like this 11, this dot goes up here. 3 11s right here. A 12, a 13, no, 2 13s. A 14, 15, and an 18. Okay. There's the dot plot. Now it says which measure of center best represents the data set. Explain why. Okay, this stuff gets a little hard to do at times for some people here. So this thing really, you know, it starts at 9 and then it adds another and then it adds another. You know, and then it does dip down, but it dips down once before it hits kind of that part, and then it's kind of clinging on to hope before it finally hits something there. This doesn't have much symmetry. It is very right skewed. in that sense. It's clustered a little more over here, and then it starts to spread out a little more. Now, it's not fully clustered. It looks like if there was at least another thing here, it would help out a little bit. But when something is skewed like this, you don't want to really use the mean, the 12.25, to talk about what's the center of the data, because the center of the data fits more around this area. The mode would almost be a pretty good number. If there were a couple more 11s, I would be more inclined to call that the mode. And in fact, that would match the median value in the end. So ultimately, we tend to not use mode. Sorry, I see something. I was looking over at my TV and I saw one of those horse masks. Sorry about that. Normally choose between mean and median. Because this is right skewed, no symmetry, it's better to actually refer to the median. And the median actually ends up being the more represented value in this thing. And look, there are some numbers over here, especially that outlier of 18, if I call it that. It's right skewed, therefore I want to call this thing the median is the best representative of 11.5 because of the right skew. That's pretty much all I'm going to say about that. There's not much more you have to say. It's not symmetrical, though. Definitely not symmetrical. Okay, use the box and whisker plot to find the given measures. Now, I'm not needing the calculator for this next step right here, so let's get that out of the way. Okay, so the box and whisker plot. Here's what a box and whisker plot tells you. First of all, there's a number line below, so these things correspond to these parts in the number line, right there. This is your min, this is your Q1, this is your median, your Q3, and your maximum. These are inner quartiles, quartile 1 and quartile 3. This represents 25% of your data. And here's the other 25%, another 25%, and another 25%. Just kind of letting you know, because I don't know if we have to describe that stuff later. The minimum's at 2, Q1 is at 5, median is at 6, Q3 is at 8, maximum is at 11. The range is the difference between your highest and lowest numbers. So the range would be 11 minus 2, which is 9. IQR stands for interquartile range. It's basically how long the box is, going from Q1 to Q3. So I get to do 8 minus 5, which is 3. They don't ask us to describe this thing at all. It's rather symmetrical, though. The whiskers are the exact same length. The median is really only shifted one way or the other here. Not much difference when it comes to that, I guess. Pretty symmetrical. And the interquartile range is a third of the entire thing. That means there's a lot of data clustered inside that interquartile range. And then it spreads out, almost like a normal curve. Okay, so there it is. Is that the only question there? Yep. Make a box and whisker plot that represents the data set. So now we need that 5-number summary. We need to find out what the min is, what Q1 is, median, Q3, and max. So we got to determine these on our own this time. And this is done by doing this. Let's start by putting the numbers in order. 25, 2 33s, and a 35. Then I got a 42, a 45, and a 56. Oop, I missed 2 33s. 2 33s, 35, 42, 45, 56. Okay. Clearly we know our min and max value now, 25 and 56. So when we put these on here, if this is 25 right here, just put a nice big dot right there. And 56 is a little more than 55, probably about like right there. That's fine. And we got our 56 value. Min and max. Cool. Now we need our median, and then we'll get our Q1 and Q3. Now the median, in this case here, we kind of just dot this way and that way till we find our middle number. Our median is 35. Which goes right here. Right here. Remember, it's a line in your box. If I look back at this thing right here, it's that line that I'm doing. I'm not going to put these dots. For some reason, I just don't do it. And what you do to find your Q1 and Q3 is that you divide the list in 2 halves. And if there is a median value in the odd number data set, you don't include the median in those halves. So I'm going to split this thing up. And here's 1/2 of the list. Here's another half of the list. And I got to find the median of the lower half and the median of the upper half, and that will give me what Q1 and Q3 are. So Q1 is the median of this list of 3 numbers here. That's Q1, which is 33. It's a little closer to 35 than it is to 30, which I clearly did not just represent that very well. There we go. And then 45 is your Q3. It's all the way over here. And then you connect this thing here and make your box and whisker plot. And there it is. It's kind of a weird set. I want to call it right skewed, except that whisker is a little long. Otherwise, I'd very much call that right skewed, very spread out. It's not symmetrical. It's more right skewed than left skewed, though. They don't ask us to describe it, but they do ask you to make it, and there it is. You don't have to put any numbers because everything else is provided for you. There you go. All right, the data set below shows the student scores on the first 4 tests of the semester. What score would the student have to get on the 5th test so that his or her average would be a 90? So they scored a 7, so they got like a C, an A+, a B+, and an A. 2 A's, a B, and a C. So here, let's find out what their average is right now. Let's just see what they got so far after 4 tests. We got 75 plus 96 plus 87 plus 94 all over 4. I'm just going to go ahead and jump into the calculator for it because I believe when I divide by 4, I just don't want to run into any issues. We're already at that time of night that it's like, you know what? Let's just keep moving along. And this calculator just froze on me, actually. It's not working. Give me a moment. Okay, let's see if she'll work any better now. Do 75, there we go, plus 96 plus 87 plus 94. Now, I don't want to hit divided by 4 right now because I didn't use parentheses. Got to hit enter first, and then divided by 4, and it looks like we're going to get 88. So the average test score right now is 88, which isn't bad. I mean, in that, like, it's close to 90 already. So they don't have to score much more here. Now, here's part of the thing before I answer the whole question here. Someone who has an average of 88 after 4 tests versus someone who has an average of 88 after 40 tests. See, if you have an average of 88 after 40 tests, you're going to have to score a lot higher to get a 90 on that test, or it might be impossible for you to get. For us here, after 4 tests, it's just fine because a large number here will skew this thing a lot better. It'll weigh it out a lot more. So here's what we really have to do. That's the current X bar. What we want to do is we want to get an average of 90. So I'm going to change this X bar here to 90. Then I'm going to average 5 tests. The first test, second test, third test, fourth test, and the 5th test we don't yet have a score for. I'm going to put an X there. Let's divide it by 5. This will give us what we need to do here. Now, I'm not going to play guess and check. I'm going to actually solve this algebraically. So first thing I'm going to do is I'm going to multiply both sides by 5 here because that side's being divided by 5 and X is over here. I want these 5s to cancel. 5 times 90 is 450. The other part is I don't have to do anything calculating these anymore because I already have a calculation for it. It's 352. There we go. We just got to subtract now. It looks like X. Looks like you're still going to have to get a high score. It looks like a 98. You have to get a 98 in order to solve this thing, in order to do it. So on the 5th test, 98% for him or her to get a 90. So yeah, you got to do really well. I mean, it's going to be really tough to do. This problem kind of reminded me of another problem. It was a problem that Einstein got wrong. I know I'm going to jump all over the place for this, but it does have to do with average. Einstein got this problem wrong. It was something like, pretend like you have this like Oldsmobile that's driving up a hill and down a hill, and they're both the same kind of distance. They're both like a mile. 1 mile and 1 mile. And here's the Oldsmobile, whatever it's driving. Vroom, vroom. Now, when it goes up to the hill, to the top of the hill, it can only go as fast as 15 miles per hour. The question that is asked here is how many miles per hour would the car have to go downhill for the car to average 30 miles per hour? Now, here's what Einstein would have done, or here's probably what Einstein did. You'd say, hey, you go 15 miles per hour for the first mile. Hey, look, because these are weighed the same, just like these tests, right? We assume these tests are weighed the same. That's why we can add them. So we assume that if these are all weighed the same, I can do my 15 miles per hour here plus my unknown miles per hour and divide it by 2, and I should be getting 30 when I do that, right? If I average my speed here with my speed here and get 30, then I can get my answer. So you multiply by 2, and you get 15 plus x equals 60. Subtract 15, you get x equals 45. So you say, okay, you can get 45, you have to go 45 miles per hour, which actually makes a lot of sense. 45 miles per hour to average 30 miles per hour overall, right? 15 for the first half, 45 for the second half, they average to 30. Mathematically, there's nothing wrong with that. And you're like, well, Einstein couldn't get that? No, the problem was the answer that Einstein put at 45. The problem is it doesn't go beyond math, but you got to see this beyond just the algebra of this problem. Some things are impossible to achieve. If you go 15 miles per hour over a course of a 2-mile road thing here, you could go the speed of light after that and you still won't average 30 miles per hour, because to average 30 miles per hour for this trip, your first, I don't know if I can explain this. I don't even know why I'm talking about it, but if you went 30 miles per hour over the course of this entire trip, or not you, but say that there was another car, say there was a nice other car that was going 30 miles an hour the entire time. Okay, if another car was going 30 miles per hour the entire time as you're going 15, guess what? When you're at the top of the hill, they are done, because 15 is half of 30. So if you're going 15 miles per hour and you get to the top while someone else is going 30 miles per hour, they've finished. So you can't average 30 miles per hour at that point because you've already gone too slow to take care of that. You won't be able to catch up. Anyway, that's something I was going to say. So what I was saying with this was that if you took 100 tests or something like that right here, sometimes you can't average a 90 because your test score here would be too high. You can't get over 100%. It's just this weird thing I wanted to make mention of. Because averages are good and great and you can calculate them that way, it just reminded me of that problem. Okay, so here's the last problem, and I know I'm going to have to use the calculator for it. I just haven't done it yet. The table below shows the heights in inches of the players on a basketball team, and inches are like 72 inches is 6 feet tall, so this person's 5'10". That's like my height-ish. And then, yeah, we have some other things. Find the mean, range, and standard deviation of the data set. Okay, so the mean is going to be adding all these things up. Now, I don't need to find the median or anything, so I'm not going to put them in order. But here we go. 70 plus 74 plus 83 plus 85 plus 77 plus 80 plus 76. Sorry, this is going to take a while. This is exactly how this thing goes. Feel free to fast forward this thing as I'm writing this. I'm probably going to run out of room right on this addition. 82, 81, 79. I don't want to do this one in my head, sorry. 81, 82, 78, 72, 84. Okay, that's all divided by 2a. 1, 2, 3, 4, 5, 6. So it looks like 12 and 24. Okay. Way too many numbers. Wow. Okay, 70 plus 74. And again, feel free to skip this part. Please do. 76 plus 83. I might get a typo. This is probably what you could have done too. 78 plus 79 plus 75 plus 82 plus 81 plus 79 plus 79. Ooh, I have a typo. Hang on. Or not a typo. There's a number I missed that I left out. I left out a 73. Hang on, let me count my numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 22, 23. Yes, I'm missing a 79 or a 73 in between these two 79s right there. Oh boy, yeah, that's scary. Plus 73. Maybe I should really count them next time, you know? Plus 81, plus 82, plus 78, plus 72, plus 84. This is all going to be divided by 24, which is 79.2083 repeating. So this, it says round to the nearest hundredths. So 79.2083 repeating. So the mean is 79.21. That's the nearest hundredths right there. Now, what I'm going to do here is, because I'm going to have to calculate this thing a lot, and I'm going to keep the exact number. I'm going to round my mean answer, but I'm going to use the exact answer every single time. It's something you wouldn't know to do, think to do, be able to do, probably. But I'm going to store this answer into a letter here. Let's do just A, because I'll be next to this every single time. So I'm going to store it as A. Okay, the range. I didn't put these in order, but did I see a biggest number? I didn't see a 90-inch basketball person. Tallest I see is 86. Let's see. You see anything higher than 86? 86 inches. That is a 7'2" individual. Like Kevin Durant style, sort of, I guess. I don't know how tall he actually is. So here we go. We're going to do 86 minus the lowest person, 70 inches it looks like. So again, that's like my height. So the range is 16. We want to be able to interpret this stuff in a moment as well. Okay, standard deviation. I'm going to do that next. But okay, the mean says the average height of the individuals here is a 79-inch person about. The range in inches from the shortest to tallest person is 16 inches. So the difference in inches between these two people is a whole foot and 4 inches. That's quite a bit, I guess. Okay, standard deviation. Now here's what it looks like. To find the standard deviation of something, you're going to take each value, pretend like that was x1. You'll subtract it from your mean. You'll square that value. Then you'll add the next number minus the mean squared, and the next number minus the mean squared. And you'll keep doing this until you get to the last number. In this case, there are 24 numbers, up till there minus the mean squared. You'll divide by how many numbers there are, and you'll take the square root of that. That's how you do standard deviation. Now, I'm going to do most of it in the calculator, okay? But just so you get the understanding in this case here, standard deviation will be, I should have written the actual numbers with that. Okay, so I'm going to do 70 minus 79.21. Now I'm going to use the exact number. I'm not going to use the rounded one. Squared plus 74 minus 79.21 squared. Main reason I'm going to do the exact one is because I'm going to show you in this calculator how it can do standard deviation. Your yellow one might be able to as well. On your test, you're not going to have something like this because you can't use a calculator. So it doesn't matter one way or the other. I just want to show you what it's going to look like ultimately. All over 24. So I'm going to compute this the old-fashioned way, though, for this particular part. So it's going to take me a while again. Skip what you need to. Skip what you need to skip. You know what's really bad about this thing is that it's hard to type all this. Excuse me. So that's squared. You know what? I'm just going to fast forward through this part of the video, if that's all right with you guys. Okay, so sorry about that. So it took me a while here. Now I got 4.13. When I do the one in the calculator, it gives me 4.22. They're about the same thing. I'm not sure why it's giving me one versus the other. I know there's more than one standard deviation formula. They have different reasons to call them different ways, especially depending on how much data there is. I'm going to do the one that I got. I got 4.13 based on it. So I'm just going to write that one down. I'm not saying the calculator is wrong. Now, you might get a different answer because you probably rounded your values here, and maybe the calculator rounded in a different way. It gets a different number. Anyway, there's your standard deviation. I acknowledge that this was kind of a long process to do. If you decided to find out how to calculate it online or something, that's totally okay. For something like this, it's more about describing it when you're being asked to. But anyway, that would be your standard deviation there. Something in the 4s, I guess. It's pretty close. Okay, and the last part here, we got to display the data in a histogram with 5 intervals. Okay, so I guess it is best if I do rank these now in a certain way. So let me first split it up into different sorting methods here. I'm going to first split up into 70s and 80s so I know what's where. So I got a 70... I got a 74, I got a 77, 76. Okay, so let's sort this down a little bit more now. Let's find 70, 72. Okay, so what I can do here is, break this up into some intervals where, the range of them is 16. Okay, so I can get... if I divide it by 3, then I'd have more than 5 intervals there. So I guess I got to divide them up into things of 4 inches maybe. So maybe I can start with 70 inches at the bottom end of part of the frequency table here. So what I'm going to do is I'm going to choose some intervals in inches and how often they occur. My intervals, I'm going to do every 4. So I'll do 70 to 73 inches. I'll do 74 to 77 inches. I'll do 78 to 81 inches, 82 to 85, and then I'll do 86 to 89. There we go. And then I can do the spread from that. So 70, 73, I got 3 people there at 72 to 73. 74 to 77, I have 4 people. So see how fast that goes now? 78 to 81, there's a lot of people. Boom. So 5, 9. 82 to 85, got 7 people there. And then 86, I have 1 person. So I can build the frequency table, or I can build my histogram based on this frequency table here. I'm going to bring it over, and I'm going to create those intervals onto here. So 5 different intervals, so 1, 2, 3, 4, 5. And this will be the 70 to 73, 74 to 77, 78 to 81, 82 to 85, and 86 to 88 or to 89. So they're all equal widths of 4 each. So frequency of 3 for the first guy here. Let's see, I can use nice little color coding. Make them a little transparent. Let's make the line black and this thing some form of like a, there we go. So here we go. So there's that one, frequency of 3. Next one is a frequency of 4. And then a frequency of 971. So all the way up here, right here, and then 1. Okay, how would you describe the distribution of this data? I wish I made this thing. I can't say for sure. Based on the clumping there, I couldn't give you the exact thing on this data either. It looks like it's more clustered there, and there's only one person there, so whatever else. So I'm sure left skewed would be a better answer, because this follows a diminishing pattern, whereas this one just drops off with an outliered individual of a really tall person. Plus, I did my data distribution different than somebody else might have, right? Based on my data here, it's looking probably a little slightly left skewed, or a little symmetric. I don't know, symmetric to left skewed. You know, these aren't always perfect. And again, if you chose different intervals, then it would give you a different result based on the 5 intervals. And that middle cluster really does bring things up there quite a bit. Anyway, that's the end of the stuff here. I'm sorry, I'm checked out at this point. There's too much to do. Okay, so you saw the final outline here. Here are the things that were covered. If you want to take a look at this again, pause at any point. This is all the things that were covered, and I know, like I said, I did these ones here as well. Good luck the rest of the way for everything that you do here, and I hope that you enjoyed the semester, everything we were able to do. Sorry that I wasn't able to make this video as optimal as you may have wanted it to be. Take care, everybody.